we have discussed this Schwarz inequality, and this gives a relation between the inner product and norm, and we have seen that the modulus of the inner product x y is less than equal to norm of x into norm of y, where the equality holds if and only if either y is 0 or x is c y, or this set is linearly dependent set, that is y is equal to c y, where c is real and greater than 0, cx where c is real and greater than 0 or equal to 0 at the most. Clear? Now, this Schwarz inequality will be used to establish the relation or establish the triangular inequality, which will be helpful in justifying the norm can be written in terms of the inner product. And in fact, when we have introduced the concept of the inner product, then we also define this norm of x as the inner product of x x under root of inner product x x, because this is a non-negative quantity greater than or equal to 0 and norm of x there. And we have seen that this norm satisfies, this definition satisfies all the conditions of the norm except the one which we have not verified, the triangular inequality. So, now once we have the Schwarz inequality, it will help you in establishing the triangular inequality also. So, let us see the triangular inequality. We want it to show that norm of x plus y is less than or equal to norm x plus norm y, is it not? So, start with this norm of x plus y whole square, and this can be put it as x plus y under the inner product sign. Now, open it. So, we get from here is x comma x plus y comma x plus y, is it not? This is, and this further can be written as x comma x plus x comma y inner product plus y comma x plus y comma y inner product. But this is norm of x square by this definition, and this one let it be as it is, x y plus y x plus this is norm of y square, let it be 1. Okay. Now, we know this Schwarz inequality says that modulus of the inner product x y is less than or equal to norm x into norm y. So, this inner product x y will be less than or equal to norm x norm y. This inner product by x will also be less than, because it is a conjugate of x y only. Okay. So, modulus of this, so it will be further less than or equal to norm of x whole square plus 2 times norm of x norm of y plus norm of y square, and that will give, okay. So, that will give you the norm of x plus norm of y whole square, and taking the square root we get the, so taking square root we get the triangular inequality established. Okay. We get the desired inequality. So, nothing to worry. Okay. Now, when this equality holds, what it says is that result, if you put it this thing in the form, I am just writing as a result, or result says the norm the norm introduced with the help of inner product satisfies this thing, norm of x is less than equal to norm x plus norm y, where the equality sign holds if and only if either y is 0 or x equal to c y, where c is real and greater than equal to 0. So, we have established this result. Now, what we want is to establish whether if the equality holds, these two conditions is satisfied. Obviously, from this side is obvious true. If y is 0, the equality is there. If x equal to c y, then we can write this 1 plus c x, and here also we can write 1 plus c is greater than 0 and the equality is satisfied. So, from here to here is nothing to prove, only when this equality holds, you have to prove that x and y are linearly dependent, or x can be expressed as a c times y, where c is real and greater than equal to 0. So, to show the equality condition, that under what condition the equality sign shows, what we do, we have taking this one where the norm x square y square is equal to this, then no, from here x by and by x I have put it less than equal to this, is it not? So, from here only the problems is coming with this sign less than equal to this. Okay. So, let us see the how we have for equality, the one equation implies that inner product of x y plus inner product of y x must be equal to 2 times norm of x into norm of y instead of less than, is it not? Okay. But is it not the same as x y plus conjugate of x y, which is 2 times norm x into norm y, and this is equal to 2 times real part of x y, which is equal to 2 times norm x into norm y. So, this shows the real part of this inner product is the same as norm x into norm y. Okay. Is it clear? So, we get 2, but Schwarz inequality says that modulus of the inner product x y is less than equal to norm of x into norm of y, is it not? Norm of y. So, we can put this thing in there, it means therefore, 2 gives the real part of inner product x y is greater than or equal to the modulus of inner product x y. Is it okay or not? Modulus of inner product x y, because this norm of x plus y is greater than equal to modulus of inner product. Clear? Now, in case of a complex inner product space, the modulus of the inner product x y this will not be less than equal to the real part of this, rather than this is always be greater than equal to real part of the inner product x by. Clear? So, and here we are getting in 3, we are getting the real part is greater than equal to this, while in this case you are getting real part is less than equal to this. So, only third and fourth shows that real part of x by must be equal to the modulus of inner product of x by. Is it correct or not? Only equality sign holds. And when this equality sign holds, and what is this? This is nothing but the norm of x into norm by, is it not? Because this will be real part of this is nothing but norm x norm by. So, which is the same as norm x into norm by equal to the modulus of inner product x by. So, in Schwarz inequality, when the equality sign is there, then either this by will be 0 or x equal to c by, is it not? Where c will be real and greater than 0. Even also c can be proved and greater than 0. Even c can be proved to be real and greater than 0, because once you are saying modulus of this inner product is real part of this, it means this will be greater than a non-negative quantity modulus. So, it is greater than equal to 0. So, once it is greater than equal to 0, replace by x equal to c by. So, we can take c outside and we get the c to be greater than equal to 0. Clear? So, this establishes the triangular inequality, that this result.
I think, sir, we can directly do it from the Schwarz inequality, as the less than equal to sign is coming from the Schwarz inequality when the norm is 0.
Yes. Then you are getting equality sign, but there is in the Schwarz inequality x equal to alpha y, where alpha may be a complex also, just a linear combination, x and y are linear combination, that is all, any scalar. Clear? So, but here it is should be real and greater than 0. So, in fact, this Schwarz inequality, this will be equal to x y is linearly dependent. When you say x y is linearly dependent, this all, and this part is not covered in the Schwarz, this portion. This portion, in fact, this we will take it in the here. For equality, we can say, because both side is non-negative quantity basically, but Schwarz, when because it is a inner product is scalar quantity. Okay. So, that is why its x and y are linearly dependent, that is all. Okay. Alpha may be any real number. So, we get 2. Okay. So, this completes your that. Now, there is another lemma which shows the inner product is a continuous function. Just like a norm we have seen, the norm is a continuous function, because we have seen that this verb, the norm is a continuous function. How did we prove this thing? Remember, the norm is a mapping, is it not, from capital X to R plus, or greater than equal to 0 of course, such that x goes to norm of x, and this norm is a continuous, means if any sequence x n converges to x, then norm of x n converges to norm of x n. So, what is required to prove is when x n goes to x, then corresponding norm of x n must go to the norm of x, and this can be then, this is true because modulus of norm x n minus norm of x, this is less than equal to norm of x n minus x, is it not? Now, if x n goes to 0 right hand side, this has to go to 0. So, it is 2. So, norm is a continuous function. Similarly, we can show that inner product is also a continuous function. Okay. In fact, it is continuous with respect to both the coordinates, okay. Jointly continuous, you can say, continuous function. Why? The proof is like this, we can say in the form of lemma. So, the result is like this: if an inner product space, if in an inner product space, we write short IPS. If an inner product space, the sequence x n converges to x and y n converges to y, then the inner product x n by n will go to the inner product x y. So, this shows the inner product is a continuous function, because the inner product, this is a mapping from x cross x to k. K is a field of scalars of x, x is a vector space. So, picked up the 2 point x and x, means ordered pair x n by n, and under the inner product this gives the value of a scalar quantity k. So, when this is a continuous function, we have to show the continuity, means pick up a sequence in the inner product x n by n type, and if it goes to x y, okay, and under the modulus, because it is a scalar quantity, then we say it is a continuous function. So, start with this modulus x n y n minus inner product x y. We are giving the proof of this. Okay. Now, this can be written as modulus x n by n minus x n by plus x n by minus x y. Is it not clear? And this will be equal to modulus x n by n minus by modulus plus, I am writing less than equal to, plus modulus x n minus x comma y. Okay. Combine these two and we get. Now, apply the Schwarz inequality. By Schwarz inequality, we get this is less than equal to norm of x n into norm of y n minus y plus norm of x n minus x into norm of y. Okay. Now, this is given that x n converges to x, y n converges to y. So, when we say the x n converges to x, y n converges to y, it is automatically inherent that it converges to a norm or to a metric defined introduced with the help of norm. So, this converges in the norm which gives defined in terms of the inner product. This converges in the norm introduced with the help of the inner product. So, this goes to 0, y n minus y will go to 0, this x n minus x will go to 0. Is it not? Y n converges to y means norm of y n minus y will go to 0, this will tends to 0, this will tends to 0. So, total it will go to 0, clear, as n tends to infinity. Therefore, this sequence x n by n converges to x y as n tends to infinity, hence inner product is continuous. Okay. Now, this gives an application, this lemma helps you in establishing that every inner product space can be made complete. That is, if we take a Cauchy sequence in this inner product and if the Cauchy sequence will be convergent, then we say it is a complete space. So, with the help of this result, one can say that every inner product space can be made complete, just like a completion, just like a norm space we have seen. If X be a norm space, then one can define the isomorphism, and then with the help of the isomorphism and the isomorphism, the norm space can be made complete, is it not? And that will be unique. So far the isometric fault is means with reference to the isometric only. So similar result holds good here. So before going for the completion, we require the definition of isomorphism. Okay. So isomorphism, we define the isomorphism over inner product as follows: an isomorphism T of an inner product space capital X onto an inner product space X delta. I am putting this, taking the same inner product in both the cases. It may be different of course, but for the sake of simplicity I am choosing same inner, otherwise we can write this as inner product and this is dash delta, both will be okay. Or you can see this also, and if you want we can put this delta. Okay. This is our one inner product, this is another over the same field of scalar over the same field K. So an isomorphism T of an inner product X onto inner product X delta over the same field K is a bijective linear operator T from X to X delta, which preserves the corresponding inner product, inner products. That is, the meaning is the inner product of T x T y under this inner product value will be the same as x y. Then we say it is the isomorphism operator. So, one is that T must be 1 1, T must be 1 2, and it preserves the operation. Now, when we say it preserves the operator, this inner product, it automatically gives you the guarantee that because of the linear part, bijective linear operator, I am taking T as a linear operator. It means that addition and scalar multiplication which is defined on capital X is also preserved under T. Okay. So, basically the T, which is an isomorphism from one inner product to another inner product, it preserves all the operations defined, algebraic structures, operations defined on X, whether it is addition, vector addition, scalar multiplication or inner product introduced on it. Okay. So, that way is it clear? Now, this list gives you a theorem. Of course, I will not show the proof. It is a completion of the inner product space. The result is, for any inner product space, X, there exists a Hilbert space H and an isomorphism A from capital X onto a dense subspace W of X, W of H, sorry, this is H. and then subspace W of H. The space H is unique except for isomorphism. What is the meaning of this? What it says is, suppose X is an inner product space. This is our X. Okay. This is not a complete inner product space. What we can say is, we can always find a complete inner product space of X, say H, Hilbert space, and an isomorphism T can be defined from X to a set X into W such that closure of W is H, is dense in H. So, a 1-to-1 mapping can be introduced from X to W, which preserves all the operations of X and W. So, basically X and W are identical space, they behave as if they are the carbon copy of each other, and once they are carbon copy, the closure of this is H. So, only the limiting points are the extra points. Okay. So, that is why we are, what we are saying is that if X be an inner product space, one can identify a Hilbert space corresponding to H, which has a subspace which is dense in H and has a 1-to-1 correspondence with has a isomorphic with X. And this representation means corresponding to X, we get a unique H is unique except for isomorphism. Means suppose there is another H is dash is obtained, which has the same property, say W dash, and then isomorphism between this and this is also there. Then this W and W dash, they are isomorphic. They are isomorphic. Okay. So, that way is there is no separate T dash. Clear? We get this. So, this is except uniqueness except this isomorphism. Is it clear? So,
Is there any technique to find out this easily, or we have to search?
no, techniques is there. We have to start with the sequence, Cauchy sequence, and the same Cauchy sequence must behave here. So, that sequence is given and identified. Okay, that can be checked. Okay. Now, this almost completes the concept. I do not know whether last time I have given the concept of subspace or not.
No, sir.
No. So, let us say the definition of the subspace of the Hilbert space or inner product space. A subspace Y of an inner product space X is defined to be a vector subspace of X, taking with the inner product on X restricted to Y cross Y. Okay. What is the meaning is, suppose X, this is be a inner product space and Y be a subspace of this capital Y, which is a subset of X. We say Y is a subspace of this inner product space if Y as a vector space is a subspace of X. Clear? And then once it is a vector subspace, then it should form the inner product also. So, what the inner product is, that Y under this, say capital Y, is an inner product space, Well, what is this? This y is the restriction of this on of x on y. This is the inner product on x. We are restricting on y. So, only choosing the point of y and same inner product I am using. So, the restriction of this gives you the corresponding inner product on y. So, if y is a vector subspace and it also forms a inner product space under the restriction on y and the inner product of x on y, then we say y with this new restricted inner product is a vector, is a subspace of the inner product. Similarly, if suppose x be a Hilbert space,
Suppose X is an inner product space, and Y is a subspace, so it must be a subset.
yes, it is a subset.
So always the same type of inner product structure can be.
Yes, can be do. Yeah, that's right. That's what is restriction is there.
Yeah, so only
But-
the requirement is that it must be vector subspace.
No, but sometimes what happens, we need not to take the same inner product here. We can introduce some other inner product, but that must coincide with the restricted one. Okay, that must coincide with the restricted one. So that's what. If H be a vector in place of the inner product, if I replace x by H, if x is replaced by H Hilbert space, then we say y is a subspace of a Hilbert space provided all these conditions are satisfied. Y need not be a complete. Okay? Here y need not be complete. So, for a subspace the completeness of the y is not required, just like a norm case B. Then we have some result and the proof runs on the same line as we did in case of norm space. What is that for? Let y be a subspace of a Hilbert space H, then the following results holds. Y is complete if and only if y is closed in H. This was also a result in case of norm space, is it not? Y is closed in H, and second means every closed subspace of a Banach space is Banach, is it not? Every closed subspace of a Banach space is Banach. So, like this. Then if Y is finite dimensional, then also Y is complete, is it not? And third is, which can be proved directly, if H is a separable space, so is Y. Means every subspace of a separable Hilbert space is separable. Separable means a vector space said to be separable, it has a countable subset which is dense in its. Okay. So, if H is given to be separable, it has a countable subset which is dense in. So, Y is a part of H. So, we can prove that either Y is the same element, or if it is not, then we can identify the set which is dense and also countable. Okay. That we did it in norm space, is it not? So, same result we continue here. Okay. So is Y. So, these results follows without any problem. Okay. Now, next concept in this is basically the uniqueness, existence and uniqueness problem in the Hilbert space. Existence and uniqueness problem. This is a very important problem, particularly used when we go for the approximation part. Approximation theory, this is a very major thing, existence and uniqueness problem. What is the existence uniqueness problem in case of say norm space, in case of the metric space? So, Suppose X be a metric space, this is a metric space X D, and let this be a M, which is a subset of X. If I take X here and are interested to find the distance from X to M, then how to find the distance? D of X M, that is equal to infimum of D X by bar, where the by bar belongs to M, is it not? This distance, let it denoted by delta. So, infimum, if it is in case of the norm space, in case of metric space X D. Now, in case of the norm space, the delta we can say it is infimum of the norm X minus by bar, where by bar belongs to M. Just distance notion is replaced by norm, because it is also length. Okay. Now, the question arises, when you are taking the distances of X from various point of M, in fact, this is the point X and here is M. What you are doing is, you are calculating the all sort of distances, is it not? And then among all distance, you are choosing the infimum one, okay? And then you say this is the distance, because that smallest among all, the greatest lower bound of all these distances will give the distance from X to M. The question arises whether this really infimum exists. Are you getting some really a point here by in the set M, where this exactly this X to y distance is the same as the infimum of this? If it is so, then we say this existence of the y is guaranteed. Then whether you have a 1 by or more than 1 by, so uniqueness y is also important. Okay. So, when you are approximating the thing and when you are going for this thing, then the uniqueness of the solution is important. When you are approximating something, uniqueness of the solution is important. Existence and uniqueness of the solution is important when you are dealing with some physical problems, because if the solution is not unique, there is no use, and if the solution does not exist, also we do not have any interest in such type of work. So, that uniqueness and this depends on the space which you are dealing. In case of the metric space, this situation is very different, varies from case to case. For example, if I take X equal to R2, okay, and suppose I take this point X here, and this is our R2 space. Let us pick up this M, say this is our M, this line. Okay. Now, if I draw this, then this will be the shortest distance. Now, if this is open interval, you cannot achieve this point, whatever the value you will get, it is only this way, that is all. But in order to go up to this point, we require the point at the end, but end point is not available. So, it means no such by is available, then we are getting no by, is it not? Because this is, or should I write like further, if there exists, it means I will write x minus by. Suppose there exists by which is equal to this. So, no by is available here. On the other end, if I picked up this thing, suppose this is our M and here is x, then draw the perpendicular. So, you get a unique by, is it not? And then it is okay, but here I am taking this one, different cases, okay. And then if I take this one and then point X is as center, then there are so many by's are available, is it not? So, infinite by. In fact, so what we see here is that in case of the metric space, the situation depends where the point is located, what is the set M, clear? We cannot give the guarantee the infimum will always exist. Even if it exists, it may not give the guarantee whether it is unique. Same case is with the norm, but in case of the inner product space, the situation is much more simpler, and we will have a guarantee if we choose M, a particular type of the subspace M, either it is a subspace or maybe a convex space which is complete, then there will be a guarantee that always this infimum will be attained by a point inside the M. That is, the existence of bi will be guaranteed. Okay. So, that is why this uniqueness and existing problem has a importance, and this space, inner product space or Hilbert space, is widely used for this purpose. Okay. Clear? So, let us see, using this we require two concepts. One is, I think, convex set. Convex set, you know, a set is said to be convex if we pick up any 2 point here, then entire line segment must lie inside it. This is the line segment. The line segment Z will be of the form alpha x 1 minus alpha by, where x is this point, y is this point, alpha is a real number and lying between 0 and 1, 0 less than alpha less than equal to 1. So, if any two arbitrary point will be picked up, then the entire line segment joining these 2 points, if totally lies inside the set, then we say this is set is a convex set. Okay. Subspace is always be a convex set. When we say vector subspace or subspace, then this is a convex set. Why? Why it is convex? What is the property of vector subspace? How to prove the vector subspace? Any 2 point linear combination must be available. So, I take the linear combination alpha and beta, in place of beta I take 1 minus alpha. Okay. So, that is why every subspace is a convex. Clear? Like that. So, this will be used. Now, we have now results which based on this uniqueness problem, the result is which is called the minimizing vector theorem. Vector theorem. Let X be an inner product space and M be a non-empty convex non-empty M B, and let M a non-empty convex subset which is complete. Complete in the metric, introduced or obtained with the help of inner product. With the help of inner product, you introduce the metric, and then what this result said, then for every given x belonging to capital X, there exists a unique bi. There exists a unique bi belongs to capital M such that delta, which is the infimum of norm x minus by bar belongs to M, is equal to norm of x minus y. It means there is a guarantee that this infimum will be attained at some point inside the M. Okay. So, uniqueness and also unique is there. So, existence and uniqueness is guaranteed if I start with a set M, which is a convex set and complete in an inner product space. So, proof. So, first we will show the existence of bi. Okay. Existence of bi. Now, this is given delta is the infimum of norm x minus by bar belongs to M. It means there must be a sequence in M by 1, by 2 by n, which goes to the infimum value, is it not? This is tending to, these are all sequences converging to x, so that the infimum is coming to be y. Is it correct or not? So, we can say that by definition of the infimum, there exists a sequence infimum, there exists a sequence, there exists a sequence by n in M such that norm of x minus by n, say is equal to say delta n, goes to delta n goes to delta as n tends to infinity. Delta n which is goes to 0 as n tends to infinity. Is it correct or not? Because this infimum is delta. So, there must be a sequence by n, so that the difference x minus by n, that is the norm of this is delta n, will go to delta as n tends to infinity. Okay. Now, we want to show, we will show that this sequence by n is a Cauchy sequence, in M. Once it is Cauchy in M, M is already complete. So, it must be convergent. So, we get a point by belongs to M and existence of by will be granted. That is the our procedure. Okay. So, how to show the by n is Cauchy? So, let us put it, let this term x n minus by n is V n, x minus by n, let it be V n. Okay. So, we get norm of V n plus V m. What is this? This is equal to this plus this. So, 2 times x minus by n plus by m. Is it okay or not? So, take 2 outside, we get x minus half by n plus by m. Now, this will be delta, infimum of this thing is delta. It means, if I remove infimum, then whatever the by belongs to M, the norm of x minus by will be greater than equal to delta. Now, here by n and by m both are the points in M, and M is, since by n by m belongs to M and M is convex, M is convex set. So, half of by n plus by m is also a point of M. Once it is point in M, therefore, norm of B n plus B m, this will be greater than equal to 2 delta. Agreed or not? Is it correct? Clear? Let it be 1. Okay. Now, consider norm of by n minus by m, because we want this to be Cauchy. So, norm of by n minus by m goes to 0 when n m is sufficiently large, then it is Cauchy. So, let us consider this square, but by n minus by m, what is this? Is it not the same as V n minus V m whole square? V n minus B m. So, what you get? Basically, you are getting by n minus y. Now, every inner product and the corresponding norm satisfy the parallelogram law. Okay. So, by parallelogram law or parallelogram equality, what we get is, what is the parallelogram? Do you remember? That is parallelogram law is norm of x 2 times norm x square plus 2 times norm y square equal to norm of x plus y whole square norm of x minus y square. This is the parallelogram identity. So, using this, this one is giving, this is given. So, everything you are writing here. So, this will be equal to 2 times V n square, 2 times V m square, and then minus sum of this square. Is it okay or not? Now, norm of B n, what is this norm of B n? Since V n is equal to x minus by n, so norm of B n equal to norm of this. By n is a point in what? M. So, this will be greater than equal to delta. Similarly, by m is also greater than equal to delta. So, we are getting this is this one by n minus by, yeah. So, this will be, no, sorry, this is delta n, I am taking delta n, sorry, let it be delta n, because this one is given x minus by n is delta n. Okay. So, here x minus by n, which is V n, is delta n. So, using this, we are taking this is 2 delta n square, 2 delta m square, okay. And then what is this? V n plus V n plus V m. What is the V n plus V m? This from 1 is greater than equal to 2 delta. So, minus of this is less than equal to. So, we add the less than equal to sign, minus 2 delta means minus 4 delta square. Is it okay? Now, as n m goes to infinity, this delta n a goes to delta, delta m goes to delta. So, entire thing will go to 0 exactly. Okay. Once entire thing goes to 0, therefore, this sequence by n is a Cauchy sequence in M, but M is complete. What? M is complete. So, every Cauchy sequence is convergent. So, this sequence by n is convergent. So, by n converges to an element y belongs to M. Therefore, existence of by is guaranteed. Okay. Now, uniqueness of by. Suppose there are two values, let by naught and by 1 are the point in M such that delta, which is the infimum of norm x minus by n, is equal to norm of x minus by naught, and this is also same as norm of x minus by 1. Suppose there are 2 points by 1 and by 2, where the unique limit exists, infimum exists. So, if it is unique, then by naught should not be equal to by naught should be equal to by 1. So, we start with norm of by naught minus by 1 whole square, and this can be written as by naught minus x minus by 1 minus x square, and again use apply parallelogram law. Okay. Once you apply the parallelogram law, you will see that this will come out to be by naught minus x whole square, by 1 minus x whole square minus by minus x plus by naught minus x whole square, and this will be, this is delta. So, this will be 2 delta square, 2 delta square, and this part, because by x can be taken outside, 2 can be taken outside. So, this is greater than equal to delta. So, we get this is less than equal to, this part greater than, yeah, this will be belongs to this. So, it is greater than. So, this will be less than equal to, this will, what is this? If you take 2 outside, you are getting x minus by naught plus by 1 by 2. Now, this is the point of by. So, it will be greater than equal to 2 delta. So, it is less than equal to minus 4 delta square, and this will go to 0. Therefore, norm by minus by 1 whole square is less than 0, but norm cannot be negative. So, implies y equal to y 1, okay? And this shows the uniqueness. That is all. Thank you. Y not equal to y 1, yeah. Okay? Thank you.